purpose of this tutorial is to review economic principles associated with the management of inventory. Inventory involves inputs that are purchased by a production system and sit idle until they're used in the actual production of a product of interest. So while they're sitting idle in inventory storage, it is costing the operation money in terms of lost capital. Now, if we look at the typical structure of how inventory changes, it's really a function of the order quantity, Q, that is purchased periodically by the operation, and then that quantity is used over time until a reordering is made. So if we are looking at an annual 12-month time horizon here, we would see that there were 3 times in which the order quantity Q was ordered, and there's a time interval between orders. Now, once we know what the quantity of Q is, we also know an important factor in that what the average inventory is. In other words, the average inventory for this input would be 0.5 or 1/2 of Q, because on average that is the amount of inventory that would be in storage at any particular point in time. So once we know Q, we also know the average inventory. Now, the process becomes a little more complicated in that most operations don't wait until the inventory goes down to 0 to reorder. They'll have a lead time in which they realize how long it takes for the vendor to supply them the input, and so they'll have a stocking reorder point. Once the number of inventory levels go to a certain level, then the manager will decide to replace an order using a lead time in terms of how long does it take the vendor to fill the order. So there's some nuances to inventory management, but at the heart, what's critical is this order quantity Q. Also, once we know this order quantity Q, and if we know what the demand or the usage of that input is for the operation, we can then determine how many orders are placed. So demand divided by Q will tell us the number of orders that are made in that period, in that year, let's say, that will meet demand. So with Q and with demand, we then know the number of orders. And so we can see that in this case there are 3 inventory points where a reorder was made. So now the cost of inventory can be divided into 2 major components. One, the inventory order cost. In other words, each time an order is placed, it costs money. An administrative assistant has to make the phone call, go check the inventory, so that takes time. And so there's a cost associated with the placement of an order. And the other cost is the inventory storage cost. This is money that's invested in idle inventory that is not at work because it's not being used in the formation of a product immediately. And so there's a loss rate of return on money that could be used for other activities that would generate an income. So if we look at the order costs first, if we know what the cost is of place in terms of placing an order, and one could estimate this from what the wages are per hour, the amount of time spent in making an order, and then we know the number of orders made in the year is dependent on the demand divided by the quantity order. So this order cost times demand divided by Q is the total order cost associated with a input that is purchased in quantities of Q over time. Now the other cost, the storage or holding cost, can also be calculated. If the time value of money is 10%, in other words, if I have the money available, I could get a return of 10%, and let's say soybean meal costs $200 a ton, then the value of an inventory unit of soybean meal would be $20. In other words, the price per ton times the time value of money. So each ton of soybean meal that sits on the barn floor or in the storage bin is costing me $20 per year. Now we know the average inventory based on the 1/2 of the quantity ordered, Q, so then we also know what the storage cost is. So on average, the inventory will be 1/2 of Q, and then that times the storage cost of that unit of inventory will give us what the storage cost is per year. So with these two values, we can come up with a total inventory cost, the sum of the order cost plus the storage cost. And then we can use calculus to determine what level of Q, what order quantity, will make this total minimal in cost. And when one takes a look at this graphically, you can see here's our storage cost. So as we increase the quantity ordered, the Q, the cost of storage is going to go up linearly, because the slope of that line will be what that cost is of per unit of quantity stored per year. And we can see that the order cost follows this red line, in that when we make very few orders it's very high, and then it decreases very rapidly as we increase the quantity Q, and thus reducing the total number of orders we have to make to meet a given demand for a given year. And of course, the sum of these two lines is the total inventory cost, and we can use calculus to find out where this slope is equal to 0 or minimal in cost, and that becomes then the optimal order quantity. And so if you work this out, the equation you come up with is that the optimal order quantity is the square root of twice the demand times the order cost divided by the holding cost. And what we've done is we've created an analytic to look at this. You can also build in reorder points, number of orders per year, etc., other related equations that are driven off of this order quantity Q. This is an analytic that is available online that you can look at, where you enter in the order quantity, maybe look at what your current order quantity is, the units of demand per year, the purchase price per unit. If there's a transportation cost, you could enter it in, but the cost to place an order, and the holding costs. And if I look at the single item, if I look at a single item, I can see here that here's my current program. So I'm ordering quantities of Q. So my total holding costs of, if I have quantities of 200, my total holding cost is $663. My order cost is 83, so my total inventory cost is 748 associated with this input. The optimal, okay, says that I should order this in units of 72 units, and that would reduce my inventory cost down to $475, so a 57% savings. There's some potential monies in terms of controlling inventory. The graph down here shows how this economic order quantity would change as we varied the amount of demand per year. The program also does the graphics that we saw earlier. So here's my order cost, here's my holding cost, and here's the total cost, and it's showing me the optimal here at 72 units to minimize my total inventory cost. One can also look at price discounts. Many times vendors will come up with a lower price but require that you purchase a different quantity. And so what this does is it looks at the total cost of, okay, the change in unit price, but also what's the associated change in inventory cost, and works out what is an optimal program or strategy that you should follow. So in this case, purchasing 100 units of the input at $58 per unit input is cheaper than purchasing, ordering around 72 units where the unit cost is $66 per unit after we consider the inventory storage. So this program allows you to change all of these parameters here and see what their impact is on various strategies. One can also change the price discounts here to reflect different options and Of course, if it gets sufficiently low enough in price, then this will become optimal. And so you can see what the sensitivity is. So I hope that you find this analytic useful. If you have any questions or comments, please feel free to contact me at galligan@vet.upenn.edu.